So to introduce the idea of ensembles, we should revisit one of the application areas that we looked at the beginning of the class. That was the idea of doing movie recommendations, which I think a number of you might have chosen for your project. Do you recall the Netflix Prize, which was a competition hosted by Netflix to improve its recommendation algorithm by 10%? If a team was able to do that, they would have won a $1 million prize. And of course, you may know that this prize was actually won. Just 3 weeks after it began, at least 40 teams that had registered had actually posted an improvement over the Netflix classifier. As you can see here, there were a number of algorithms that people had tried, including ones from particular research institutes across the world. The top teams had showed about 5% improvement, so it was getting there. Even though there was initial excitement, improvement slowed. Everyone wanted to get to the 10% improvement to get the progress prize of $1 million. You can see the leaderboard here showed how things progressed. At the beginning, there was a research team from the University of Toronto that was doing well. But later, there were 2 individuals that banded together to create a machine learning algorithm that did fairly well, and that persisted all the way until mid-2007. In fact, it's quite fun to read this account of how the Netflix competition went about, so you can read about it here. As performance improved, we could see that individual algorithms couldn't do that great, so people started mixing things together. Here was a team called Rookies, and they said, thanks to Paul Harrison's collaboration, which was another team at 22, a simple mix of our solutions improved our result from 6.3% to 6.7%, which was a pretty big nudge in the right direction. Another person who was at rank 8, Eric Paratek, said, my approach is to combine the results of many methods, also two-way interactions between them, using linear regression on the test set. The best method in my ensemble is regularized singular value decomposition with biases, post-processed with kernel-rich regression. So the idea of combining multiple methods together seemed like a good idea. Another team that has a very humorous name is when gravity and dinosaurs unite. You can see that the 2 component teams of Gravity and Dinosaur Planet came together to create a learning algorithm that blends the results. Of course, we might have guessed that from the name itself. In fact, the winning team actually was an ensemble that put together several different approaches. The team that won the competition, which is Belcore's Pragmatic Chaos, is a combined team of 3 different component teams. Belcore consisted of Robert Bell and Yehuda Koren and Chris Walensky. Chris Walensky is one of the people who documented the progress of the Netflix challenge. The members of Pragmatic Chaos and Big Chaos together also formed a part of the team. And they said there were 2 main factors which improved overall accuracy. Basically, the quality of the individual algorithms, as well as blending them together using ensembles. Best blending results are achieved when the whole ensemble has the right trade-off between diversity and accuracy. So this is a very important concept, and this particular slide encapsulates a lot of the details that we're going to be seeing in the ensuing part of the post lecture. How can we combine several different classifiers together? There are several different ways. We could support the most trustworthy of them based on their usual performance. That's what we have been doing through the use of validation. We just have several different runs, and for each of the models, we just select the one that works the best. Instead, we could do voting. We could have all of the T different classifiers individually report whether they think a stock would go up or down, and we can have a vote between them. We could also weight those votes if we believe that certain algorithms or certain analysts that might be represented as an algorithm have better results than others. We could do that using a tuning parameter, alpha, which would be specific to the particular analyst, or algorithm being used to make a decision on whether to buy a stock or sell it. Finally, we could combine these predictions conditionally. For example, if one classifier says sell, we might ask another set of classifiers whether to buy or sell. Actually, we just finished this idea using decision trees. The idea behind decision trees is exactly that, where we have a single node in the decision tree called a decision stump, which makes a decision, and we basically array all of these stumps together as a tree. These are all models of blending, where we're aggregating the output of the hypothesis after we've trained individual models, usually using some form of training and validation. A key component of this is that all of the component hypotheses need to be diverse, as we saw on the mention by one of the Netflix winners. If we have learners that are diverse, we can counteract the problem of having classifiers that are overly specialized and have high variance. But that's not the only thing we can do. We could perhaps obtain H while we're doing the learning process itself. What might that look like? Let's see in the next section.